Okay, I ended part two of isokinetics on this plot where I was talking about the importance of understanding the direction of the angular velocity, the direction of torque, and the direction of joint power. Knowing that angular velocity and torque are vectors, and these directions describe each of these parameters, whereas power, joint power, is a scalar. And so these directions, although mathematically, algebraically turn out to make sense, but giving context to the positive and negative sign is a little different than understanding the direction of these vectors. So remember, power is a scalar, and there's two equations that we use. Power is force times velocity in the linear world, but in the angular world, power is equal to the product of torque and angular velocity. Torque is the same as moment, or in this case, I like to talk about joint torques or joint moments, and as we move more towards applying this to human movement. All right, so to understand this, and if you remember, I hesitated when I drew out the the torque profile for the quadriceps during the knee extensor movement. And I hesitated because I did not explain fully the reference frame that we need in order to give the direction of joint power some meaning. Okay, so let's take a step back and let's look at reference frames. All right, so reference frames. So typically, I start with this reference frame, and the vast majority of our problems that we deal with, this reference frame works fine. Where we have a spatial plot X and Y, or we would have a third dimension coming out of the board, out of the paper here. And generally, I always use up is positive, forward is positive, and if we're dealing with the rotation, counterclockwise movement is positive. And in general, these reference frames work well as long as we set the problem up in a way that it makes sense. So this dealing with torques really highlights the importance of choosing a reference frame. So this is the way I like to assign the direction of a torque is I draw a lever system, I identify the axis of rotation, identify the force, and then I take a look at the direction that that force would tend to rotate this portion of the lever around that axis of rotation. And I use a counterclockwise is positive reference frame. And if the rotation is counterclockwise, we would assign this torque to be positive. And the math of that all works out, and that's all correct. The problem with this is, and a limitation with this simple approach, is if we're looking on the other side of this lever. Okay, so rather than standing looking at the lever from this side, let's just pretend we can go inside the paper and look at the lever from the other side. And what we would actually see is this, the same situation, but just from the opposite side. Here's the axis of rotation, the lever, here's the same force. And in this case, the way that we're looking at it, this would tend to rotate the lever in a clockwise direction because now we're looking at it from an opposite side. That would be, given this reference frame, a negative torque. Nothing wrong with that. It's perfectly fine. All our math questions will be answered correctly, and there's nothing wrong with that. However, when we start dealing with human movement, and sometimes we look at the movement from the right side, sometimes we look at the movement from the left side, using this simple approach can sometimes get us in a little bit of trouble. Or at least it complicates things a little bit, and there's an easier way to go. And so that easier way is rather than identifying counterclockwise movement is positive, counterclockwise rotation is positive, what we will do is we'll assign an anatomical movement a direction and give that some context. So in this case, what we'll say is wherever we see a flexor torque, also known as flexor moment, these are the same thing, that's a positive torque. So now we're assigning the direction of torque, the direction of the torque vector, to be positive or negative based upon what direction that torque is tending to act. So here's the upper arm, and so now extensor moment will be negative, given this reference frame. Here's the upper arm, here's the forearm, here's the bicep brachii pulling on the forearm, and from this side, that torque would tend to rotate the forearm in the counterclockwise direction. If we just use that reference frame, that would be positive torque. If we looked at this from the other side, that would be a clockwise torque, and that'd be a negative torque. So things get mixed up a little bit based upon which side we're looking at the human body. So to avoid that confusion, what we do is we say this bicep brachii is trying to cause flexion at the elbow. So we're going to call that a flexor torque or a flexor moment. If the tricep were active here and pulling on the electron arm process to cause extension, we would call that an extensor moment, and that torque would be assigned a negative direction. All right, and it doesn't matter which side we view the human body from. If we see the bicep acting, causing the forearm to move or trying to move the forearm through flexion, that bicep is always going to be a flexor. That tricep will always be an extensor. That bicep will always be assigned a positive torque value. It doesn't matter which side we're looking at the human body from. So this ends up being a little bit more meaningful when we start trying to interpret moments, and ultimately as we start moving towards joint powers. Okay, so the importance of reference frame becomes really critical. As you're reading the research, I want you to pay attention to the reference frame that the authors are using, both from an angular position perspective as well from a joint moment perspective. All right, so that's really where we're headed here, is to understand joint moments, also known as, AKA, also known as joint torques. I flip back and forth between these two terms, and you know how much I stress terminology. You would think that that's laziness on my part. Well, it probably is lazy, but these two sets of terms are used a lot in the literature, and so sometimes you'll see this, sometimes you'll see this. So I try to use both terms, to always mean the same thing. Moment is a little better math term, has a little bit more meaning from the physics perspective. Torque is probably more the classic term that we used, probably more common now to use joint moment. But what we're really trying to do is work towards understanding joint power. Because when we start understanding joint power, we're understanding how, now we know what power is, rate of work done, but conceptually we know power is the rate of transforming energy from one form to another. All right, now you can also transform energy from one object to another. So this becomes a really interesting and important parameter to understand, because now we're looking at what's happening at a specific joint. So if we're looking at someone cycling and we calculate the joint powers at the ankle, knee, and hip, we may be able to tell a movement strategy of that person is they are knee dominant, right? Meaning that they're generating most of the power at the knee joint to propel the bike forward. Whereas other cyclists may have more of an ankling technique where they rely more on ankle power, or in others maybe more hip strategy, hip dominant. All right, but now what we're doing is we're getting more specific at understanding the strategy that the person's using based upon power, rate of work done, or how quickly we're transforming energy from one form to another. But power is a scalar, okay? So the importance of understanding algebraically what a positive or negative power means, we really need to stick with understanding our reference frame. All right, so now here's this plot. This is all the same set of plots as what I've done: angular velocity, torque, and joint power. We stack these plots on top of each other. And now let's go through a little bit more the example I did with isokinetics. We talked about the person sitting on the bench doing a knee extension exercise. And we can use counterclockwise as positive for angular velocity. And we would know that we did use, and we will use anatomical position 0, and flexion angles are increasing, and therefore extension angles are decreasing. Using that reference frame is independent of which side of the body we're viewing movement on. And the beauty of that is a negative velocity will indicate that we're going through extension. A positive velocity will indicate we're going through flexion. Okay, so this is extension. If the velocity were up here, that would be flexion. But right now we're doing extension. And then if we looked at a torque moment, and you remember I hesitated because I drew what I would see on the computer, and that's the way the software works. But in reality, what we want to do is set this up so our reference frame is a flexor moment is positive. We're going through extension, and we're using the quadriceps to cause extension. So the moment at the knee due to the quadriceps is an extensor moment. Therefore, that moment is negative, okay? The negative sign indicating that this torque due to the quadriceps is trying to cause extension, which that's what the quadriceps does. It's an agonist for extension at the knee. All right, so that's that. Now, if we go down to joint power, we use our equation, P equals T omega. Power is the product of these two, but power is a scalar. But now, given that we use this reference frame, flexor moment is positive, and we used anatomical position is 0 and flexion angles are increasing, the product of these two yields a direction which can have some context now. So now when the direction of power is positive, what that means is the joint moment and the angular velocity are acting in the same direction. That means that the quadriceps are trying to cause extension, and we're going through extension in this example. That means the quadriceps are contracting concentrically. All right, so positive power, negative times negative would be positive, that would be positive power. And we would say it's a concentric contraction of the quadriceps, and we're generating power, right? That's a funny way to say it, but that's what we're saying, is that we would be generating power to cause knee extension. And this is a situation where torque and omega have the same direction, and these two are vectors, all right? Algebraically, it comes up to a positive value. That's positive power, and that positive sign indicates that we're going to have a concentric contraction. So how do we have a negative power, and what does that mean? Well, negative power algebraically is the moment and angular velocity have to have different directions. So if I look here, and let's say that we're still going to have a negative moment due to the quadriceps, because the quadriceps are an extensor. But now let's say we're going through flexion. What's going to happen is the leg, the segment between the knee and the foot, would start coming back towards the table. We're going through extension, but we're contracting the quadriceps. So that's indicating an eccentric contraction. So the beauty of using anatomical position is 0, flexion angles are increasing, and flexor moments are positive, is that those reference frames are independent of which side of the body we're looking at or viewing from. And then that gives power, the power sign, a context in terms of indicating either concentric or an eccentric contraction. So I've just drawn out the eccentric situation here. So here is angular velocity. Positive velocity indicates flexion, given our reference frame. So now remember, it's an isokinetic dynamometer. So I go in and I set the machine to be some value, 50 degrees per second, all right? That value indicates the machine will move only at 50 degrees positive, which would be flexion. So we're going to be going from an extended position to a flex position. We're starting from 0, so the machine does need to help get the leg moving. But once it's moving, it will always move at that velocity. And while and this movement's going to actually happen in a way while the quadriceps are trying to resist going through flexion. And that's the beauty of these machines, is I can set it up so that the quadriceps act eccentrically through flexion. I could also set this up to have the hamstrings fire and go through flexion, but the hamstrings would be acting concentrically. Okay, so there's some neat ways that you can set up this isokinetic dynamometer, because now I can test the strength of the quadriceps acting through extension, through concentric and eccentric contractions. All right, but let's just look at our math here. I've got a positive angular velocity indicating flexion. I still have my extensor moment, which is negative. I take the product of those two and I end up with negative power. So we end up with an eccentric contraction. Or sometimes we would actually say we would be absorbing energy, or we would have power absorption. Okay, oops, something like that. Okay, some different ways to describe that kinetics. Now, don't lose sight that this is still isokinetics, and yes, we're going through flexion, but remember, this is our angular kinetics equation. Our quadricep torque plus our resistance torques equals I alpha, which is 0, because alpha is 0, because we have constant velocity. So we rearrange this. The quadricep torque is equal to the resistance torque. That's what isokinetics is all about. And the key with this is no matter how hard the person pushes, either through concentric or eccentric contractions, the machine will adjust how much resistance torque there is so that angular acceleration is 0. We can set it so we're going through flexion, or we can set it so we're going through extension. But in both of these examples, the knee, the quadriceps are acting, in this case, eccentrically, in this case, concentrically. All right. And that's the beauty of these machines. They will allow or control the movement to be either in one direction or the other, based upon creating the right amount of resistance so that angular acceleration is 0. The part that often is left out in textbooks is you have to increase velocity from 0 to something. So this would be speeding up in the negative direction through extension. And then once you hit a certain velocity, that velocity is constant in extension. This would be speeding up through flexion. Then we would stay at that velocity. And then at the end, we'd have slowing down through reflection to 0. And likewise, slowing down through extension to 0 here. But we only look at that isokinetic region when we're doing an isokinetic analysis of muscle. Okay, so what's new in this is I've introduced this idea of a different reference frame where we're describing moments based upon the direction of the movement that the muscle wants to make. So the muscle is contracting, causing a torque about a joint, and the muscle will either cause that action and act concentrically, or it will oppose an action and act eccentrically. And to understand that, we just need to look at the velocity, or we look at the power value, whether or not that power value is positive or negative. Okay, I hope that helps. And I'll do some more work on power in sports to follow this up. Thank you.